Okay, hi, I'm Chuan Yang, and today I'm going to be deriving the formula for the Euler's IVP.
Okay, so we'll basically be writing dy dx equals to fxy for here lah. And since we don't know how the graph actually looks like, we'll just use this random graph here. And right, so now we're trying to we trying to find the gradient at this point here. So x0, y0, so it's this point, and then we use x1, y1, which lies on this tangent line here. Okay, so basically a straight line is a tangent line lah. Right. So it's the formula here, which is y1 minus y0 equals to mx1 minus x0. We bring y0 to the other side by adding it on both sides. So y1 equals to y0 plus m0 times x1 minus x0. So m0 is basically dy dx equals to, which is also equals to fx0 y0, and x1 minus x0 is the step size, right? This can be written as dx or h, whichever one you want to call it. So the smaller the step size, the more accurate the linear approximation. So we'll sub everything back into here. We get y1 equals to y0 plus fx0 times h, and yn plus 1 equals to yn plus h times fxn yn.
Hello, so hi, we're going back to the Excel sheet. This is my 5th attempt, I'm crying. So basically, dy dx equals x squared plus 1 over y, that's the thing we're given. We're going to solve that. So h equals to 0.00000001, so our step size for now is a small value to get a more accurate linear approximation here, like, as one of our hypotheses. Yeah, that's what I'm saying for now. So, right, step size is small. So here, y0 equals to 1, we'll sub x equals to 0, fxn yn equals to 1, and yn equals to 1 here. And then from here, we'll use E5. We'll find E5. Basically, it's our yn plus 1 is equals to yn plus h times fxn yn. So, yn is equals to E4, as you can see in the formula here, plus $d$1 is our step size here, times d4. And d4 is this value here, which is our fxn yn. Okay, it's going well so far. Next, second part, we're trying to find our fxn yn, which is this formula here, x squared plus 1 over y. So, what's our fxn yn? Essentially, we're subbing in c5 into x and y into e5 into y. So that's all. Alright, so this is the value, the answer for this part, 1.9148504. That's the answer for the step size equals 0.0001. So when you use a step size of 0.05, we end up getting an answer of 1.912934. And I'm going to say first, the formulas on both sides are the same. So yeah. Okay, anyways, coming down here is how we solve the first order differential equation. So dy dx equals to x squared plus 1 over y times y on both sides. We'll get y dy equals to x squared plus 1 dx. Integrate both sides times 2. We'll get y squared equals to 2x cubed over 3 plus 2x plus c. And then we sub x equals to 0 we'll sub x equals to 0 for y0 equals to 1. And y equals to 1 into this equation here. We end up getting c equals to 1. Sub it back into this equation here. We get y squared equals to 2x cubed over 3 plus 2x plus 1. So at y1, we are subbing in x equals to 1 on both sides. And then we square over both sides to get y to isolate y. So y equals to the square root of 2 over 3 plus 2 plus 1 is 1.9148542.155. So here we can see that the smaller step size, when our step size is smaller, is 0.0001. We get 1.9485037 compared to when the step size is 0.05. We are now getting 1.91293432. Oh, I'm rapping right now. So we can see that the smaller step size, the more accurate the answer, because this value is clearly closer than this one. So here's a graph just for you to see. This formula here is actually a linear graph because it's a straight line. Alright, that's all. Bye. Hey, wait, let me end.